Okay. No. Okay, let's consider some aspects related to design now. Let's look at the blocks below. We have two types of engineers typically involved in the manufacturing of a chip. One is the circuit designer, which designs the digital circuit, digital or analog in general circuit, and one is the process engineers, the process engineer, which of course follows the fabrication process. Of course, the two have to talk, because the circuit design has to design something that can actually be fabricated, and also the process engineer must understand what the circuit designer wants to do, and in order to allow them to talk, we have a set of design rules, and these design rules ensure that what the designer sends to the process engineer can be actually fabricated, and lets the process engineer be sure that the circuit will be fabricated as designed. There are essentially two types of rules. They are determined by the process, the fabrication process, and in particular one of the most important quantities defined by the design rules is the minimum line width. So the minimum width of each line of the patterns that can be realized. And of course that depends on lithography, on the capability to expose the resist, and on the process, which is the capability of etching away the layers after the exposure. And the design rules are given in terms of micron rules, so absolute quantities, absolute dimensions for the intra-layer layouts and for the inter-layer layouts. So intra-layer means lines belonging to the same layer, and inter-layer means lines belonging to different layers. These rules have to be are specified, and have to be followed by the circuit designer, otherwise the chip will not be fabricated as expected. So the concept is pretty simple. For example, in a 0.25 micron CMOS process, 0.25 is from 1992, if I remember correctly. Just to consider a simple CMOS process, we have several types of layers. Typically in the layout they are indicated by different colors in order to distinguish them. We have 5 different layers of metal, from metal 1 to metal 5 in different colors. Then we have the N-well. The 0.25 process is an N-well process, so you just have one type of well, the N-well. Then there's the polysilicon, and then there are the contacts and the vias. The vias are the contacts between two different metal layers. So you have via 1 to 2 is the contact from metal 1 to metal 2. If you need to electrically put the two of them in contact, and so on. For every two adjacent layer you have a different type of via. And W, PW are the doping for the contacts. Then we have the active areas, and the M plus and P plus are the high doping for the source and the drain of the PMOS and of the NMOS. So again, anyway, it's not really important to remember all the layers. Just remember that we have many of them. Then we have the intra-layer design rules. For example, for each layer, let's consider, for example, the end well. We know that the end well cannot be smaller than 1-2 point micron in each dimension, and must be at a distance of at least 0.6 micron. Okay, this is a type of intra-layer design rules. Tells me if I want to define wells, how big I have to make them, and at what distance. Then I have the same type of design rules for the polysilicon, for the metal one, and so on. For example, for a polysilicon, this is interesting to consider. The minimum width is 0.24 micron. The process is 0.25 micron. The minimum width of the polysilicon is the channel length of the MOSFET. So, of course, that in a 0.25 process, it has to be almost 0.25. So that is the minimum. I cannot make any gate length smaller than that. And of course, I have also the minimum distance between two different metal lines. In this case, is 0.32, and so on. You should be able to see that the higher we go with the metal lines, the bigger they have to be. So these are the intra-layer design rules. One has to check that in the layout that is given from the designer to the fab, all these design rules are satisfied. Of course, this is done automatically by a so-called design rule checker, which is a program that has to go through all the mask designs and to check if all these rules are satisfied. And then, in addition to that, we have the interlayer rules, the minimum dimensions between two different layers. For example, this is a transistor layout, is a PMOS transistor. You see, this is the poly, which defines the gate, and then the P+ regions define the source and the drain regions. Okay, so of course, the P+ region goes also over the poly, because when we make the ion implantation, actually we dope the silicon with P+ for the source and for the drain. We dope the polysilicon, and this is something that we want, but also the polysilicon acts as a barrier, so the silicon that is below the polysilicon is not doped, because it blocks the ion implantation. The ions remain in the polysilicon and do not go below it. But still, you see, we need to define at least what's the minimum distance between the end of the P+ region and the side of the poly, and what is the minimum distance if I want some distance between the P+ and the poly between the two. Just to let you understand why this is important. This is extremely important because there's a lithographic step, then all the processes are done, then the wafer is put again into position, and there is another lithographic step, and there is no possibility of having the two steps perfectly aligned. So if we do not allow the P+ region to go at least 0.44 micron beyond the end of the poly, we cannot, let's say, we cannot take into account some alignment tolerances, because, for example, there might be some misalignment, and then at least if you make them 0.44 micron, you're sure that the poly is in the middle between the source and the drain. Okay, these minimum distances are made in order to take into account the fact that that some misalignment is possible. Just to make an example, if there is some misalignment between the poly here and the P+, okay, then you do not have a transistor anymore, because the drain and the source are short-circuited. Okay, so with at least 0.36 micron, you are sure that even if there is some misalignment, you still have a transistor. Okay, this is the let's say the concept. And of course, you have all of them for all different situations in which alignment is important. And of course, alignment is important if you want to contact a metal one with another metal, and you need to superpose them in order to put the two of them in contact. Okay, so this is the reason for which there are some micron rules. This you should be able to recognize it now. These are two inverter in series. You see, probably it should be clearer now than it was at the beginning. You have the metal one, the contact, the poly line, that is the two gates. Then here we have the PMOS. This is the NMOS. Then this is the contact with the P well. This is the contact with the N well. This is ground, and this is VDD. And then we have another inverter in series, and so on. Okay. How these layers are realized? Typically, we have a layout editor that basically allows to draw the different layers, and let's say associated to the layout editor, there is also a design rule checker that checks if these minimum distances are satisfied between different layers, and it really checks them in line. I mean, as a spell checker when you write a document, more or less it's the same concept. Okay, this is another way of, I mean, it's not important, it's just a curiosity. This is another way which one often find in order to define an inverter. Again, it's called the stick diagram. You only see the type of layers, but there are no dimensions. It's only important for the topology, for the relationship between the different layers, the connections, but not the actual lengths and widths. Okay, I want to make some reference now to the packaging, which is something that we have not seen up to now. Just a few basic things, because the package is in practice extremely important. You have to consider that in a cheap integrated circuit, typically the package is much more expensive than the actual silicon chip, and this happens because, of course, the package has some important functions. It has several important requirements. From the electrical point of view, it must add few parasitics, and that is particularly important for the chips that have to operate at high frequency, because sometimes the operation frequency can be limited by the package, and the higher the frequency of operation, the better the package has to be in terms of low parasitics. This is very important for high performance microprocessors, and also it's very important for radio frequency chips, for wireless radio transmitters, receivers, and so on. Then the package has to provide mechanical robustness to the chip, because the silicon die itself is extremely fragile, and the mechanical robustness is only provided by the package. The next very important thing that a package must do is remove the heat. Okay, because the silicon chips typically goes very high in temperature during operation. A high performance microprocessor can go as high as 150 degrees during operation, but not higher, because it will not work anymore at higher temperatures. So the package must be able to remove all the heat fast enough. Of course, it can be helped with a fan or with some other cooling mechanisms, but at least the package must be able to keep the pace of the cooling mechanism in removing the heat from the microprocessor. And finally, of course, it must be cheap, because in many instances the package is more expensive than the chip. So probably you have seen also in these videos you have seen some of the packages, but I want to mention now the possibility of bonding techniques, because of course the package must also provide a way to connect the internal contacts on the silicon die to the external pins of the chip, and this is a very specific issue, and there are different ways to do that depending mostly on how much you want to spend for the package and how many pins you have. The easiest way is called wire bonding. Basically, this is the silicon die where the chip is. On the periphery of the die, one usually puts the so-called pads. The pads are metal areas that must be contacted in order to connect the signal with the outer world, so with the external pins of the chip. And this is the substrate of the package, onto which the die is fixed, typically with some glue. And then there's this die had some leads that are connected to the external chip, to the external pins of the chip. These are the pins, the external contacts of the chip. And you have to keep one-to-one relationship between each pad and an external pin, and typically you do it with gold wire. You bond a gold wire on the pad and on the lead, and this is done manually for a small number of chips, or of course in large scale production is done by robots automatically. Gold is used because it has a high conductivity. You do not need so much gold, so it's not that expensive. And the problem is that this is not good for high frequency operation, because this gold wire has some inductance, because it's a long wire, and which for sure has significant inductance and high impedance at high frequency. And this of course introduces some unwanted behavior. Typically can strongly limit the frequency of operation of the chip. So this is done for simple things, not high frequency ones. It's the easiest way to do it. For example, in the lab, when we have to put chips into the package, we do it in this way with a manual bonder. Okay. When we typically design chips, of course, we cannot fabricate them here. We send them to an external foundry. Then we have them back cut already into pieces, and then in order to measure them, we need to put them into packages. So this is done with wire bonding in our case. This is something which allows for some more automation. Is not really something for high performance chips. It's called tape automated bonding. Basically, you start with a tape that already has all the wires in place, and you put the tape onto, you glue the die onto the substrate of the package. This is the package substrate. This is the die on which you have the chip, and then you put after you have put the die on the substrate, you put the tape on top, and I mean, if you are precise enough with the alignment, you can bond at the same time all the pads. Typically, in order to obtain electrical connections, you need a solder bump, which is let's say a ball of metal, which can at high temperature, so is quite almost melt, is relatively plastic, and then you can use it to solder the die with the external bond. And finally, there is the let's say most expensive technique, which is because you do not have wires, and then you can use it also at high frequency, is the so-called flip chip bonding. Basically, you have to flip the die, so the circuit is here on the bottom. You have some pads on the top, pretty large pads, and this is the package. These are the interconnections to the external pins, and then you use solder bumps in order to put in electrical contact the pad that you have on the chip with the metallic contacts of the package. And that is very good for high performance chips, because of course you have the shortest possible conductors, so you have a very small inductance, and therefore even at high frequency the impedance of this conductance is not significant. Okay, just to I think I have a picture here just to illustrate what we no, this one. Okay, this for example, this shows you this is something that we have done here in some months ago with the flip chips. Basically, you see below, you can see some structures, and of course we did not remove anything because this is a working chip. You see the shape of the uppermost metal layer, and then on top of it you have an insulating layer, and then you have the bumps that have to be connected with the package. So this is just before the connection on the package. We made a photograph with an optical microscope. Okay, so the chip is I mean, in the total die is twice this one. In this image, I just wanted to show one part of the total die. Okay, let me just go back to. Okay, these are simple things just to finish this topic. Of course, once you have a package, you need to put the chip on the board. So assume that this is the board, then you have to, this is the external pin and this is the chip. Of course, it's just a package of the chip. The real chip is inside. Then you need to solder the chip on the board, and typically you have two ways of doing it: with through hole mounting. So you have this pin that passes through a hole, and then it can be soldered to this contact, or with the typical situation now for high volume and dense boards is with surface mount. So basically there's no passing through the board, and this allows to have boards with both sides full of chips, and it's the typical situation now. Of course, in practice, everything is done very automatically with a high degree of automation, For small volumes it can be done also manually, but it's really, you need to be almost an artist to do that. Okay, and this is just an image. You're probably familiar with this, at least if you have ever opened, if you have ever looked at the motherboard, you've seen many of this situation. This is something that we have seen also in the video. This is called dual inline. Dual DIP stands for dual inline package. This is the die. You typically have bond wires in order to make the connections, and the pins are on two lines on the longer sides of the package. There was an example of this type of package here, and these other packages are for the surface mount. Oh, these packages are connected to the board through holes, and these other ones are for surface mount. Also, this one is for holes, this is for surface mount. It's that's it. And it's just for completeness. Okay, now is much more common than before to have multi-chip modules, or also so-called system-on-chip modules. System on chips. System on chip. System on chip. SoC. Just to mention, this is an acronym that you can find easily if you look at some electronic magazine or so on. In that case, in a single package, you have more than one die. So basically, in a single package, you have almost a board. You have chips that come from different dies that are glued, fixed to the substrate of the package, and then are interconnected in different ways. Typically, the interconnection is provided by the substrate. It's really patterned on the substrate, and this is much more. It's very common now because it allows higher integration, so more computational capability in less space, and also enables to have smaller interconnections that are good to operate at a high frequency. Just to mention something that I've already shown you, but when we have seen the main the processor of the iPhone 6, the A9, in the same package there are two dies. In one die there's the microprocessor, and in the other die there's the DRAM. Okay, and they are in the same package. So this allows to have the DRAM and the microprocessors very well together, very connected, and to let's say minimize the access time to the memory. And it's become very common, especially if you want to have a high degree of integration. Okay. Now, my feeling is that I should stop now. I can stop now, and yeah, because there are only a few minutes. There's no reason to start another